This video was produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. Previously, we looked at the probability of a specific event, and we said the probability of the event is equal to total number of successful outcomes over or divided by total number of outcomes. Now, we will look at how often an event happens, the probability of an event with its long-run relative frequency. The formula for relative frequency is very similar. Relative frequency is equal to the total number of successful trials over total number of trials. An example of relative frequency might be how often a football team, say Man United, win against another football team. For example, Chelsea. If Man United has won 20 games out of 30 games they have played against Chelsea, the relative frequency of them winning would be 20 over 30, or 2/3. Let's take a look at a relative frequency question. The question states that a gambler always uses the same die. The die was thrown repeatedly and the number rolled was recorded. Using the data in the table, can you tell whether the die is biased? If the die is unbiased, there should be an equal relative frequency for each number. As we know from rolling a die, we are equally likely to obtain a 1, a 2, a 3, and so on. To answer this question, we will calculate the relative frequency for each number. From the relative frequency formula, we need to know the total number of trials. To get the total number of trials, we will add up the frequency. So 10 plus 5 plus 8 plus 3 plus 9, and we'll get an answer of 50. So there were 50 trials in total. The relative frequency for 1 is the total number of successful trials, in this case 10, divided by the total number of trials, 50. Usually we write the relative frequency as a probability value. So 10 out of 50 is 1/5, which is 0.2. Now we'll look at the relative frequency of rolling a 2. The number of successful trials is 5. The total number of trials is 50. So 5 over 50 is a tenth, or 0.1. I'll quickly fill out the remaining values. Now we have all the relative frequencies for the die roll. We can see from the table that the relative frequencies are not equal to each other. In this case, the highest relative frequency is 0.2, so the die is biased towards 0.2. However, is this a fair test? If we throw a die 6 times, we will rarely get all 6 values. Increasing the number of times an experiment or trial is repeated generally leads to better estimates of probability. In this question's case, we conducted the experiment throwing the die 50 times. If we had thrown the die 500 times, we would get more accurate relative frequencies. Also, it should be noted that the relative frequencies add up to 1. So if we add 0.2 all the way across to 0.3, we will get a value of 1. Following from the relative frequency is the expected frequency. The expected frequency is the number of times an event is presumed to occur on average in a given number of trials. For example, if we toss a fair coin 100 times, we would expect 50 heads and 50 tails. The expected frequency of an event is equal to the probability of that event multiplied by the number of trials. Now we'll look at a question on expected frequency. Using the data in the table, what is the expected frequency of the coin landing on heads when tossed 500 times? So we want it to land on heads, and using our formula, the expected frequency is equal to probability. So the probability of a head is 0.4 multiplied by the number of trials. In this case, our number of trials is 500. So 0.4 multiplied by 500 will give us 200. So if we throw this coin 500 times, we would expect 200 times for the coin to land on heads. The other 300 times the coin would land on tails. We can double check this by calculating the expected frequency of tails. In this case, tails would be 0.6 multiplied by 500, which does indeed give us 300. That concludes this discussion. That concludes our discussion on relative frequency and expected frequency.